So this is getting a bit dated, but mid last year we had, just to brag a little bit, to show you that you can do a lot of very good things with HDF5. NetCDF audios are very similar in some ways, but there's no reason to believe that you can't achieve very, very, very close to peak or very close to peak I/O bandwidth when using single shared file with HDF5 on a big HPC box. So you got to kind of tune it a little bit. Wasn't a tremendous amount that they did, but they did have to kind of tweak a little bit, and a lot of it was kind of kicking muster to make certain it was doing the right thing at the right time, too. But you can use HDF5 to do whatever scaling you'd like. So we'll talk a little bit here about some of the nuts and bolts, the mindset behind Parallel HDF5, the requirements that involves, show you some very simple, straightforward parallel programming, because it can get very complicated very quickly. Talk a little bit about performance analysis and parallel tools, and if I have some time, talk about other features. So one thing I want to make certain that we stress a little bit is the difference between MPI I/O and HDF5. MPI I/O is really low level. It's just linear byte stream. It doesn't have any metadata, it doesn't understand, these guys have covered it earlier, but you have to do all the work. You have to interpret that byte stream and figure out what it means and where your bytes are and where the arrays are and what the dimensions are and how all that format is defined. It's all in your own. It's also defined in what they call it's external 32, which is the standard interchange that's portable. But everything else would be machine dependent, according to the standard. And technically, external 32 is defined as big endian, which is weird these days, right? And if you really were going to use these features in MPI/I/O, which are not terribly well implemented, just to confirm. Yeah, I know, it's crazy. Yeah. So anyway, there's just limits with things you can do with MPI. So in comparison, HDF5, I covered this a little bit earlier, but it's much higher level. It's data management. We're not just looking at bytes in the thing. We do the data and metadata according to the format spec. It's very self-describing. And each machine, you can put it in your own native representation and then take it to a different platform and get all that information back out. All the conversion and everything is handled by HDF5 automatically. So when we were building HDF5, it was designed from the beginning with Parallel in mind. This was a collaboration between NCSA at the time and the Department of Energy and NSA labs, Livermore, Sandia, Los Alamos. We've broadened out significantly since then, but that was the original collaboration to design HDF5. Want to make certain that you could do multiple processes at the time. At the time, it was not really very obvious that MPI was going to win. So we kind of gambled, we felt, on MPI at the time. But that was the goal, is that everybody would see a single file image. We didn't want to do a file per process because of the post-processing, all the different problems when you move between numbers of processes, and you really clobber the file system. So we wanted to use the standard Parallel I/O interface, what turned into MPI, and the output, the files that you create, had to be portable between platforms. So settled on MPI. Fortunately, MPI/O was there in time for us to use. And the files that you create with a Parallel HDF5, you can either access those directly from a serial if you've got access to the shared machine, the shared file system, or just deliberately FTP them or copy them somehow from one place to the other. The file format is identical between the two things. You can easily get at it any which way you want. Earlier we were talking about the requirements for Parallel I/O. You need MPI. We don't have any other way of talking about Parallel I/O right now. Talked about some other kind of more advanced things and done a few prototypes, but right now the main production way to go at it is you need MPI. It's going to have a decent MPI I/O, and we break them every single year, several times. And I email Rob, and he goes, "Oh yeah, good idea," and very good about fixing things in MPitch. You need a parallel file system, otherwise it's kind of pointless because you're it all into one disk. So something like GPFS, Lustre, PPFS, whatever your parallel file system of the current day is. But those are the, those should be there on your HPC systems already. So nothing new or unusual there. Generally speaking, looks a lot like what you'd expect. You'd spawn an application that uses HDF5 across all the compute nodes. Those make calls into the HDF5 library. Internally, we will make calls to MPI to do I/O or communication, whatever is necessary. Turns into a large, probably, HDF5 file on the parallel file system. And then somewhere in the storage architecture, it's got all kinds of fanciness that you've seen from the Argonne slides already today. So about what you'd expect, I would say. Nothing unusual that we do. We don't put any extra layers in there. We don't try to do collectives on our own. We don't do two-phase I/O internal to HDF5. We bet heavily on MPI, and we leverage it strongly. Spend a moment a little bit about consistency semantics, because they're a little weird, and you don't get what you think you get. Not that it's our fault. But these are the rules that define the outcome of multiple, as it says here, possibly concurrent accesses to an object with multiple processes in the system. So Parallel HDF5 basically defines a set of consistency semantics that are aligned completely with MPIO. What a surprise. And these basically define, when you make changes to one part of the HDF5 file and another with one process and another one tries to read what you've just written, what are the rules for making certain that that happens without getting a bad write or a bad read or inconsistent data in some way or another? Here's something that you think should work but doesn't. I guarantee you think this works and it doesn't. Or at least it doesn't guaranteed to work. If you do a write on one process and then you wait at the barrier, right? For process 1, say, okay, process 0's write has to complete, the barrier occurs, everybody's cool, and you read over here, no guarantee. Sorry, that's how MPI works. There's some special rules that you have to do to make this absolutely certainly work. And we haven't been caught yet. And I would really complain a lot if this broke. But there is no guarantee in MPI that that works. Because process 0 could be just as easily caching some of that data that you wrote, even though a barrier occurred, and the guy doing the read on process 1 just gets stale data from what's sitting in the file. Currently, this is fine. But if you really want to be certain, MPI has some atomicity guarantees and a sequence of calls. If you call sync and then barrier, a regular barrier, and then file sync on your file, MPI will guarantee that your data gets transferred across all the nodes. Everything is consistent at that point. If you don't do that, there is really no guarantee. It may be fine. It probably is. But there's not a guarantee. So HDF5 does basically that. It says, hey, we give you this way to turn atomicity on if that's what you want, which will kill your performance, by the way. Don't do that. Sorry. And then we provide a sync call that you can do the barrier sync, basically call, if you really, really need it. If you're debugging something weird and this happens to you, it's probably not the problem. But it's an option if you really, really, really need it. Yes, sir?
Yeah, so I understand that you were kind of highlighting this little feature of MPI, but are you actually suggesting that we do message passing through files?
Oh, that's something you should not be doing. I'm just saying. But people think that you can do those sequence of calls and it would be okay, and it's not okay. So you have MPI, right? Send the silly call through the real communication channel. That's the right thing to do. But to just expect disk to act like memory. So don't worry about this too much. But should you ever get caught out, there's a nice document that we've got here that says, hey, here's all the interesting details about this part of the problem. I'm only highlighting this because you're here and you care about parallel I/O, right? I mean, normally I don't even mention this in my talks. So talk a little bit about the programming model for HDF5. We have wrappers, but again, they're just shell scripts. You can do all this by hand if you want. It's fine. Some of the parallel HDF5 things that you have to be thinking about. We open the parallel file with an MPI communicator. We have to call MPI file open. It requires a communicator. That's part of the setup for creating an HDF5 or accessing a file in parallel. So we're going to give you back a file handle, and then you got to go at it through the file handle, which is what you'd expect through HDF5 anyway. All the process, I mean, collective is collective, right? Everybody, when we say it's collective, everybody that passed in that communicator is going to duplicate the communicator, and then all those processes have to participate in future parallel I/O collective calls. You can open different ones with different communicators, that's fine. But everybody that opened that file with that communicator has to participate in collective calls. So this is probably the biggest gotcha that people run into when they do collective HDF5. This and how to set up collective data element rights. Anything that modifies the metadata, the structure, the graph, the hierarchy in an HDF5 file, all those calls are collective. You have to have everybody in sync and keeping the view of the file identical. You can't have one guy say, hey, create this data set, and this guy over here and say, create that group, because then they're out of sync and they get confused. So some things that aren't totally obvious like that, when you extend a data set, you're modifying the file in a structural way underneath the covers. So this setting the extent for a data set, that's collective as well. There's a very nice list. It's very comprehensive up on the web. You should go look at that if you have a confusion or question about something. The data set element, the array data transfer calls, they can be collective or independent, very similar to HDF, or MPI. But, regret is 2020, right? We didn't change the file name, or the function name, we just changed the parameter that you pass in. So instead of MPI says something, 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 all, and it's really obvious what's going on, HDF5, when you do a D-read or a D-write, a dataset read or write, you have to look at the parameter for the dataset transfer property that says, hey, was that a collective property that got set or something else, independent, a default one. So you won't see H5D write all. You'll see a sequence of calls that lead up to that saying, do collective I/O on the next dataset write that uses this property, and then you pass that property into HDF5. I'll show you this. So once you've got all this working, what do you get? All the pieces of the file, it kind of acts like a file system. You know, everything in the file is accessible by all the processes. All the objects are there. Everybody can come in and look at the arrays, write pieces to them. Individually, you can update them, or collectively, you can update an array altogether. And in fact, we've got some features that are similar to PNetCDF's write combining stuff that I'll show you in a little bit too, where you can do multiple data sets at the same time, one single giant I/O call. So I should probably put H5Pi up here as well. It's starting to get in there. But basically, C and Fortran, we support anywhere that you probably will go with your application. Typical sort of places that are in the big HPC centers these days. I said this a little bit earlier, but you're basically going to use the property list in HDF5 because the default model with HDF5 is serial, sequential access. That was where we focused on making it simple for people to get in and get at things. And the optional behavior, the parallel I/O, is accessed through the property lists. So you're going to set up the file access property list to use MPI/I/O, then open the file and access the data and close it. I'll show you what this looks like here. So the red parts here are the parts that are different from a sequential program. So you have your obvious MPI, init, and finalize. Fine. This piece here, we're setting up a property for file access property list, a FEnabling. So you're going to say, hey, on that file access property list, make certain that I do MPI/I/O for that file access property. We're going to pass in the communicator and the info objects that you want to use to open that file later, and then pass in that file access property list to the creation call for HDF5. So this used to be something like H5P default before in the sequential version of things, right? Now we're saying, hey, I have a special property list. I'm going to put that in for my access property there instead of the default call. The rest of this is kind of similar. You know, this data set create, that'll have to happen on all the processes in your application. Then a little bit later, we go create our data set transfer property list. And we say, hey, on that transfer, when I use this transfer property list, I'm going to use it. I want you to do collective I/O in HDF5. And then you're going to pass that transfer property list into the data set write call. And again, this used to be one of the default property list parameters, and instead, oh, we've got a non-default thing that we're doing. We're doing collective, because HDF5 defaults to independent, and we're going to pass that in as the property. Structurally, you could build that, populate it with some data, and it would be fine. You have a basic HDF5 programming, parallel programming code here. Question?
Is there an issue if you have, like you compile this code and you run it, but you have, the file system is not, it doesn't allow for MPI?
So the question is, what do you do? What happens if the file system doesn't allow parallel access with MPI? This will be, you know, your maybe MPI init fails. I don't know. Right. MPI is there. Yeah. Well, I test on my Mac, right, too, and it's not anything. It's got multiple cores, right, but it's not really a real parallel box.
Exactly.
This is fine.
Okay.
Yeah.
So no
do this all the time.
Okay.
Should be fine. It's possible that the MPI implementation could barf at you and say, I don't know how to do parallel I/O on that storage device, but it would be MPI beefing at you, not HDF5. Yeah, this should be good everywhere, pretty much. So a lot of what you're going to be doing in parallel access with HDF5, you're going to have, hey, I got pieces of these things on different processes, so let's try to get into that a little bit more here. Again, go hit the tutorial. Lots of great stuff, more than I can possibly talk about here. Great examples to go look at. And by the way, we've got a help desk that is manned, you know, basically 8 to 5 every day of the week, not on the weekends. And there is a phone number, but I'm not telling you. I mean, you could call, but don't. It's just help@hdfgroup.org, right? Very simple. Just email help. Help desk will get back to you and say, hi, okay, you've got this, and they'll point you to the problem, or they'll work with you to try to work out what your issues are. If it gets into like a big multi-day debugging thing, we probably can't help you that much. You're going to need to get a support contract, right? We're small, we're nonprofit, we try to be really pretty lean, but you can get a decent amount of help and certainly good pointers to examples and other people having the same, you know, issues. She can refer you off to the HDF5 discussion forums for the developers and things like that. So hit the help desk, hit the tutorials on the web, and hit the help desk. But for those of you who are here, basically you're going to have each process, you're going to define some selection. We're going to use the select hyperslab call. Then we're going to execute a read and write call using those hyperslabs. You can do them collectively or independently, that's fine. I'll describe a few patterns that you can use that are moderately common in terms of parallel jobs. And I'll show you a little bit of code. So just for example, if you've got an application that's writing, you know, each process has a couple of rows that they want to write out. This is relatively silly data, but the colors are basically indicating what you're trying to do. And so this is certainly possible. You can write out columns if you want from different processes, interleave them if you'd like, that's fine. You can write out fun little checkerboard things. You can do blocks, which is a little more structured and a little more normal for what I would say would be likely. Any kind of complex data pattern that you'd like, we don't care. You're just going to describe it to us in terms of the elements that you've got in memory and on disk, and we're going to go build an MPI data type and go whoosh, and send it off to disk. Piece of cake. You can do irregular, funny shaped things and disjoint whatever. So more examples here. So the goodies here. If you want to do high performance parallel HDF5 code, I'm probably going to give you a bunch of pointers here, but I'll try to hit the high points. I mean, I've only got 18 minutes left, right? So, wrote a paper about this. go read the paper. It's got good suggestions. It's getting a little dated. It's from 2012, I think. But basically, it gives you the right framework for saying, hey, make your data this big. Here's the settings that you want. Do independent versus collective. How to manage the metadata cache. Some specific I/O system hints that are getting a little dated now, but the HDF5 stuff still stays very valid. Number one thing you're going to want to do probably is collective I/O instead of independent I/O. When you do collective I/O, you have a chance to have all the processes get together and build the funny I/O pattern that you made that was every other element that you're going to go write. And if you did that on disk, you're going to go seek, write, seek, write, seek, write, seek, write. It's horrible, right? But if you give it a collective I/O, then the MPI has a chance of saying, oh, hey, you just filled in all the gaps in the other guy's stuff. I'm going to go gather these buffers together in memory, build a nice block, and do one I/O instead of 50,000, right? So that's going to be your number one thing. And again, we conform to what MPI says collective is. Collective does not mean synchronizing. I think that's been hit on pretty well. But it doesn't mean we're going to stop and do anything and wait for other people. It just means that you got to all be here together so we have a chance of doing the communication to organize the data. It doesn't necessarily mean we're going to wait or block or do anything bad to you. And you got to get the ordering right. I mean, don't do a collective. You call A and then B on one process, and then B then A on the other guy. Because you're going to get, it's not going to match, and you're going to hang your application. So get the orders right. Same thing. Independent is not collective, right? It's kind of a poor definition, but still. So for a small example, there's a bunch more in the slides here. I'm skipping over a bunch of things. We had a user reporting, golly, this independent transfer is really bad, and they're also writing these really long, straggly rows of things, or columns of things to their HDF5 data set. So this one column was being written by one process, and another guy was writing this one, another guy was writing this one, another process that one. So you can see that it would, I'm not going to try stretching. So it would seek to here, write an element, and then it would seek to here and write an element, and seek to here. So it's doing like 230,000 individual I/Os, right, from each process. So if there were 6, it's like 1.5 million individual I/Os. So collective I/O just makes all this go away. The columns get combined, the independent calls get all combined, and the insanity that you were running into. And it's a small data set, right? This was crazy. This was just megabytes, 3 megabytes. And admittedly, it's a little while ago, but independent I/O will crush you. Almost always, it's better to go with collective. Doesn't solve everything, but most of the time, it's the right thing. So in HDF5, you have to set that up with a data transfer property list. When it's collective, we mean collective. Everybody's got to be here. And as Rob was saying earlier, you can define some of those processes to say, hey, I don't have anything. I have to participate, but I've got a null selection for this I/O. I'm just jumping through the hoops with you so that we don't hang up and get everybody blocked waiting on a communication somewhere in the background. We do break collective I/O in HDF5 sometimes. So when we have to do a type conversion, if you've done ints over here and floats on disk, MPI doesn't do that. So we have to stop, flip everything around, break it up into buffers, and we just break collective I/O. It'll happen independently at that point. Your I/O will succeed, everything will be fine, it'll just be slower than you thought. Same thing for compression. In certain cases, when you do chunk storage and parallel I/O and it gets a little complex, and we wonder what you're really doing, like 10,000 processes are writing to that chunk and only one is over here, we might break collective I/O on you and say, nah, you're going to do independent, and those guys over there, they're going to go ahead with their collective thing. I basically showed this to you earlier, so I'm not going to spend any time on it. When you create the file or you open the file, either way, you have to set up the file access property list to do parallel I/O, and then set collective and then use it. But just to recap, this is the magic invocation, right? Collective I/O. You get down to, and you say, hey, did you actually do collective I/O for me? Or that was really slow. Did it work the way I thought it would? So we put in some more kind of traceability calls. You can go and look at the dataset transfer property list that you passed in after the dataset I/O call. So after you do a dread or a dwrite, you can query on that transfer property list that you passed in, the one where you set collective, right? And you can query that back out and say, hey, did you really do collective I/O? And we'll say, yeah. Or no, it got broken into independent. And if it got broken independent, you can say, okay, why did it get broken independent? Did I accidentally do a type conversion there in memory, or was my data set compressed or something funny? So you can kind of debug, figure out why HDF5 is doing something funny. And same thing if we break it for collective to independent on chunked I/O. So similar queries. So these are good magic. These are important pieces if you're trying to figure out why you're getting poor performance from collective I/O and HDF5. Take a look at those calls. And email the help desk, help@hdfgroup.org. This is in the slides. That's in the slides. A little bit, if you're trying to say, hey, will HDF5 do pretty decent performance for me? We have a parallel I/O performance measurement tool. It's kind of like IOR from Livermore, I believe. LBNL, one of the two. That's you compare POSIX I/O versus MPI I/O versus HDF5 I/O. So you could set up apple-to-apple comparisons of what would happen if I just use MPI, how much faster or slower, is it the same as HDF5? And of course, your app is probably going to do something a little more complicated than the really simple array write that we do here, but it gives you an idea of what's going on and what the differences are. Ton of more resources here. Again, the tutorial, here's the help desk again, right? Couple touches on new features. I don't think I'm going to get all the way through this because I'm going to stop for questions. I alluded to this earlier. We're going to add these H5D multi-read and multi-write calls to the next release coming out in November. And they basically allow you to gang together as many data set reads or writes as you'd like. So if you open all your data sets and you've got 7 of them open, you're going to do I/O on all of them. You're going to write all your X coordinates and then all your Ys and Zs and pressures and temperatures and everything's going to disk. Then you can do that one. You can structure your data in the model in the file the way you want it, but still get the high bandwidth, high performance I/O that you really want. Similar to the PNet CDF write combining stuff that Ram talked about earlier. And when you get into a fairly significant number of data sets, or if the size was bigger than this really trivial size, you get a nice payoff. It's about an order of magnitude. This is small, but still. There's a problem with the way HDF5's format was designed 18 years ago. We'd used this truncate call, and that's really bad in MPI. It's really bad. It's so expensive. Just anecdotally, we were doing some testing recently on a code on the Blue Waters machine at NCSA. A few thousand processes. The I/O time for running that code with and without this fix, the close time when we do the truncate went from 2,500 seconds, 2,500 seconds down to 20. It was about a factor of 100 better when you eliminated this truncate call. Really, really painful. So that'll be coming along soon. But it's a change to the file format, so it's got to go in the next major version. It's not going to go in any of the patch releases that we normally update. So it just happens to be that way. Kind of a grab bag of other things. Currently, we have this habit of crushing the file system. When you do object opens, we do them all independently. It does tend to generate a bit of an I/O storm, and we're trying to refine that so that we can do a signal process to read the metadata for an object and then bcast that with the fancy high-speed interconnect over to the other processes rather than having 10,000 processes all go wah and grab 500 bytes, right? A couple other layers in here, but I think it might be smart to wind up here and answer questions. Any more questions? Went through very quickly, but there's 120 slides out there on the website for you.
Is there a limit on the maximum chunk size?
There is a limit on the maximum chunk size. It's 4 gigabytes currently. But that's...
On each processor, I can't have it.
No. Maybe you're thinking the selection size in memory on each process, not the data set in the file. Which you used a term that I just fell into, sorry. No, as long as MPI can handle it, you can go as big in memory as you'd like. Now, this is the places where we broke MPI. So MPitch is working on some patches to this to fix so you can get above 2 gigabytes. And this, in fact, was recently in the MPI3 standard that we have large data type support and things like that. So it's still very kind of bleeding edge if you're going to go over 2 gigabytes from a given single memory to disk. But collectively, over all the processes, you can get terabytes and petabytes, whatever you want. Just can't quite at this moment. 6 months from now, you'll be fine, right? Get over 2 gigabytes per process. Just an MPI limitation, really.
What extent the 2 gigabytes is by HDF?
Well, it doesn't really have anything to do with HDF5. There were places in MPitch and other MPI implementations that used 32-bit integers for sizes of stuff. So they had to get fixed and worked out all the places where we could stumble across.
Counts of things.
Counts of things.
So the standard uses a native integer size for counts of things.
Yeah.
Period.
Right. So
will be changed to 64 or?
Well, yes. Rob have been working on this. So we send them bug reports, and they say, try now. And then we break it somewhere else, and then it's mostly worked out. Anything else? We've got a few minutes.
Does it support multi-thread for each processor?
We didn't talk about multi-threading at all here, right? So we support multi-threading on, well, when you build HDF5, you can build it so that it's thread safe, which means that you can use any number of threads in serial or parallel, so we're safe from that. However, we do that with a single lock, a semaphore on the library itself. So when you have multiple processes running, or multiple threads within one process, the first guy in, he'll grab the lock and he'll prevent the other threads from doing HDF5 calls. And then when he's done with that I/O and leaves the library, he releases the lock and the next thread can come in and do something. So you don't have a concurrent access to the HDF5 library right now from multiple threads. We've talked about changing that, but I have a sense that asynchronous I/O would be better. As if you had a way to come in from one thread, schedule an asynchronous I/O call, and then leave very quickly instead of waiting for the I/O to happen. That would be a whole lot better, and certainly a much smaller set of coding changes than 300,000 lines of code I have to go make thread safe. So it is thread safe. You can build it that way. It's just not concurrent within a single process right now. Multiple processes, that's fine, because we use MPI and it handles the communication. Everything's okay.
So like multi-thread, multiprocessor will be?
Should be fine. You'll just have a concurrency issue where only one thread goes into HDF5 at a time. Which could be tricky if you're trying to do an MPI collective op, right? Because it's not going to work the way you think it will. And one guy will come in and then he'll be sitting there waiting for the other processes to come in and join him in the barrier or whatever we're using internally. And so you're going to have a little bit of problem that way, I'd guess. Very, very rarely do we see anybody complaining about that, though. So if you have a thing, send mail to the help desk, and we'll see what we can do. Anything else? Yes, sir?
Why is your truncate so slow on Blue Waters?
I don't know. It's whatever the file system is doing. It's pathetic. But it's bad everywhere. Everywhere we go. It's the metadata where everybody has to go in and say, hey, I got to wait till the whole file system stabilizes and everybody agrees that the file is now n bytes in size. So it's this giant shuffle back and forth between the metadata servers and whatever else is going on in the file system. It has nothing to do with us. It's not even an MPI thing. It's all about the file system.
Which machine is this?
Blue Waters. But we had it happen on Hopper. And
it's an order and truncate operation. You're truncating on every OST.
something like that, yeah.
No, but even though we changed it so that only one person sends the request to change the size, Quincey's, no, he did that, it looks like 5 years ago. I don't know if Cray didn't pick it up or if it's a luster issue is all I'm trying to get at.
But it's order n, it's not order n squared, is what you're saying. You still have to hit all the OSTs.
I'd like it if it was better. I'd like it if it actually was, and I wouldn't have to go fiddle with the file format, but fine, I got to go fiddle with the file format, so okay, good. Yes, sir?
Are there non-blocking rights?
There are no non-blocking rights at this point in HDF5. We've talked about doing an asynchronous I/O kind of thing, which would get us to that place. It's not quite the same as the non-blocking in MPI or in PNetCDF. A little more pure async, schedule an operation for completion, get a token back, and then test and wait on the token. That's where I expect we'll go. But again, we don't always get to do exactly what we want to do. Sometimes it's where the funding takes us. If you have a really good patch, I'd like one. Yes, sir?
Is there any potential issues in storing transient simulation data from number of different processors in an effective manner?
I wouldn't expect there to be any difficulty. The slide I was showing at the very beginning, 120,000 nodes, close to peak I/O on Hopper. I mean, there's a checkpoint, so it should be fine. I would expect it to be okay.
Now, if you have large data, what is a better approach? Is to store everything into a huge file, or to have several files where you are going to store part of the data?
The question is, do you break your data up into multiple files or a single file? Yeah. At this point in time, given the current scenarios that we have, that multi-terabyte file that we created at NERSC was kind of painful. It was fine. The I/O performance was fine, but like the archive system kind of went, you want to move 30 terabytes here in one file? How are we going to handle that? So they had to do all kinds of fancy restructuring of the storage archive in order to be able to move the data off from scratch, right? So it was kind of a little annoying. Performance is fine, but it was a data modeling discussion between the application and the storage guys, and how were we going to manage that? So it's not really necessarily even an HDF5 discussion. We can do it, but it's a matter of, can your system handle it? Is your app set up for it correctly? What's my analysis pattern going to look like, and how am I going to get to that data later? So you got to kind of look at the whole workflow a little bit more and think about how you really want to do your data. We can do that from HDF5 any which way, but sometimes you might prefer one way or the other. Yeah. Sorry, no magic. Yes, sir?
Did I see, so you can't do the compression if I'm doing collective writes?
Yes, that's correct. Right now, we don't support collective I/O on compressed data. And the reason why is that it's really an engineering issue, I would call it. There's no research. It's not interesting from a mathematical or programming standpoint. It's just got to get some funding to get it done kind of thing. Because all the processes have to kind of get together. They have to do, hey, I've got data for this chunk, and everybody gets together on the data for a particular chunk. So there's got to be this kind of scatter-gather thing that goes on. Then you have to compress those chunks, decide on the sizes of all the chunks that just got compressed, and then collectively allocate some space in the file that's correct so you don't stomp on each other's feet, and then go do your I/O. I just told you how to do it, right? I know how to do it. I just don't have code to do it right now because it was never like, we have these features in HDF5 and probably in other open source packages that are like, yeah, that's really cool. I want that, but do this other thing first. And I cannot tell you how many times parallel, collective, chunk, compressed I/O has been on the second on my, do this other thing first list. But again, a patch would be great.
I mean, so that seemed like a really nice feature that you guys had there, the compression. I mean, so now, and because you said, the collectives are really essential in the good performance, do your users right now who want to compress things just do sort of their own sort of quasi-compression?
Yeah, you can do it. You can do compression in the app ahead of time, and then just lie to HDF5. This is an array of bytes. Yeah, you can do that, but then you're doing all that work that I just described to you on your own somewhere. So it's not very scalable in terms of numbers of applications you're going to go implement that in. You could get us a little bit of funding. We'd be happy to do the work. Collective, yeah, it's doable. Right now the apps either skip compressing or give up collective, one way or the other right now. Yeah, sorry. I could do it. I know how to do it. But see, we got, 2 minutes over. One last question? Anybody with a high priority